So, have you ever actually wondered how an artificial intelligence predicts the future? And I don't mean crystal balls or magic here, I mean practically. Can a machine predict continuous real-world quantities, like tomorrow's house prices, or maybe the exact concentration of PM 2.5 pollution coming from a wildfire, using just a simple straight line? I know it sounds almost too basic to be true, but this exact question is really the gateway to understanding all of modern AI.
Welcome to The Explainer. Today, we're diving right in to demystify the core mechanics of how a machine actually learns. We're going to step away from the buzzwords for a bit and look at the oldest, simplest, and honestly, arguably the most influential algorithm in machine learning history: linear regression. Okay, let's jump into this and see how a basic geometric concept transforms into real predictive intelligence.
Here's our roadmap for today. We'll start with the prediction problem, then measuring machine mistakes. Third is the engine of learning. Fourth is memorizing versus understanding. And finally, we'll go beyond the straight line.
All right, Section 1, the prediction problem. Picture this. You're an environmental scientist. You've got data from hundreds of past wildfire events, and you know the total burned area for every single one. Now your goal is to estimate the average PM 2.5 air pollution concentration that's going to result from a future fire. Notice that the answer we want here isn't just a simple yes or no. We want to predict a continuous numerical value. In the data world, this is what we call a regression problem. If we plot all those past wildfires on a graph, let's say burned area on the bottom, pollution on the side, you'll notice the dots aren't just random, they actually form a general direction. So imagine placing a transparent ruler right across that cloud of data points. You aren't forcing the ruler to touch every single dot because, well, real-world data is pretty noisy, but you are placing it where it captures the overall trend. That transparent ruler, that is the physical embodiment of linear regression. Now, computers obviously can't just grab a physical ruler, right? They need math. And the formula that powers our digital ruler is good old y equals mx+b. I know it might give you algebra class flashbacks, but it's incredibly intuitive. Think of it like taking a taxi ride. The intercept b is that $5 base fare you paid just to get in the car. The slope m is the $2 per kilometer charge. Your input x is the distance you travel, and the prediction y is your total fare. In machine learning, the computer's entire job is to figure out the absolute perfect base fare and per kilometer charge to best fit the data it's looking at. Which brings us to Section 2, measuring machine mistakes.
So this brings up a really critical question. If a computer draws a line, how does it actually know if that line is any good compared to reality? Like, if it guesses a house costs $300,000 and it actually sells for $320,000, that's a mistake. The machine needs a numerical way to score these mistakes. Now, we could just look at the absolute error, which is simply the raw size of the mistake, totally ignoring whether it was too high or too low. But data scientists usually prefer something called mean squared error, or MSE. By squaring the mistakes, literally multiplying them by themselves, two amazing things happen. First off, positive and negative errors stop canceling each other out. And second, massive errors get heavily penalized. A mistake of 10 units suddenly becomes a penalty of 100. This forces the machine to pay very, very close attention to its biggest failings.
If you're wondering how data scientists grade these models, they have a few go-to metrics. MAE gives you the average mistake in simple, original units, like dollars or degrees. MSE aggressively penalizes those big errors, like we just talked about. Then there's RMSE, which takes that penalized score and applies a square root, essentially bringing the number back to normal readable units. And finally, R squared. This tells us the percentage of the variance our model actually explains. A perfect model gets a 1.0, which means it explains 100% of the data's behavior. Moving right along to Section 3, the engine of learning. Okay, so we know how the machine makes a prediction, and we know how it scores its mistakes. But knowing you have a bad score doesn't magically tell you how to get a good one, right? How does the machine actually improve the line? To answer that, I want you to imagine you're standing on top of a mountain covered in super thick fog. You can't see the landscape at all, but your goal is to reach the lowest point in the valley below, because down there, the lowest point represents the smallest possible error. The catch is, all you can do is feel the ground immediately beneath your feet. If it slopes downward to the east, you take a small step east. You recalculate and you take another step. This vivid metaphor describes the incredibly famous optimization engine known as gradient descent. Let's translate that metaphor into an actual algorithm. Mathematically, the gradient is kind of like a compass. But here's the twist. It points up toward the steepest increase in error. Because our machine wants to reach the bottom of the valley, it deliberately steps in the exact opposite direction of that gradient. So it measures the error, calculates the gradient, steps backward, and repeats this loop thousands of times until it finally reaches the bottom of the valley. We call that state convergence. But here's the tricky part. How big should those steps be? That is determined by something called the learning rate, and it's an incredibly delicate balance. If your learning rate is too small, taking tiny little baby steps, it's going to take the machine forever to reach the valley. But if your steps are too large, the machine might literally jump right over the valley and land on the opposite mountain. Choosing the right learning rate is an absolutely critical decision when training any AI.
Now, processing millions of data points for every single step down that mountain is exhausting. That's why we have a few variations. Batch processing looks at all the data before taking one single step. Stochastic processing frantically takes a step after looking at just one data point, but modern AI largely relies on mini-batch gradient descent. By looking at small groups of data at a time, it perfectly balances computational speed with a really stable, reliable path down the mountain. This keeps the AI from getting stuck in shallow, fake valleys, what data scientists call local minima.
All right, Section 4, Memorizing versus Understanding. So we've trained our model, the error is tiny, we're good to go, right? Well, hold on a second. If a machine perfectly connects every single historical data point on our graph, has it actually learned anything useful? Or has it just memorized the past? There are two big traps here. The first is underfitting. Imagine a completely horizontal line that just totally ignores the obvious trend in the data. It's way too simple. But the opposite trap is overfitting. Imagine a wildly twisting curve that flawlessly hits every single historical data point. It looks perfect on paper, but it's completely useless. It just memorized the random noise and historical quirks of the training data. When you expose an overfitted model to new, unseen test data, it's going to fail catastrophically. The true goal of AI is generalization, capturing the real underlying trends so it can confidently navigate the future, not just memorize what already happened.
Finally, let's look at Section 5, Beyond the Straight Line.
Up to this point, we've kept it simple with just one input variable. But, the real world is messy and complex. Let's bring back our wildfire pollution example. Burned area matters, absolutely. But what about wind speed, wind direction, humidity, temperature, distance to the monitoring station? If we only use burned area, we are ignoring a massive amount of reality. And this is exactly why we use multiple linear regression. We feed the model all these independent features at once, and it learns the unique mathematical contribution of every single interacting factor, combining them into one incredibly robust prediction.
But what happens when nature just completely refuses to be a straight line? What if pollution levels spike initially during a fire, but then eventually level off because of atmospheric limits? Well, for that, we use polynomial regression. By introducing squared or even cubed terms into our math, we essentially allow our rigid mathematical ruler to bend and curve gracefully. It's still using the exact same regression learning engine we've been talking about, but now the line can naturally trace the complex curves of real-world phenomena.
Before we wrap this up, we've got to remember one absolutely crucial thing. Machine learning is not magic. It's math bound by rules. For any of this to work, we have to assume the relationship is actually somewhat linear and that our observations are independent of each other. We look for normally distributed errors, and we really try to avoid multicollinearity, which is basically just a fancy way of saying we don't want input variables that are essentially clones of each other. Remembering these assumptions is vital. Applying linear regression to the wrong kind of data is literally like trying to start your car with your house key. It's just not going to work.
So, we've seen how measuring mistakes and walking down that optimization mountain powers everything from a simple straight line all the way to massive neural networks. But I want to leave you with a bit of a provocative thought today. What if we abandon lines and math equations entirely? What if a machine could learn simply by asking a series of logical yes or no questions, exactly like a human reasoning through a problem? Well, that fascinating concept leads us directly into our next topic, decision trees. But that is an explainer for another day. Keep learning, and I'll catch you next time.